The greater the air resistance, the flatter you should make your angle to compensate for it. What is a mathematical model? When one examines the solution to a physical problem, it is often, though not always, possible to draw a clear distinction between the contributions made by science and those made by mathematics. Scientists devise a theory, based partly on the results of observations and experiments, and partly on more general considerations, such as simplicity and explanatory power. Mathematicians, or scientists doing mathematics, then investigate the purely logical consequences of the theory. Sometimes these are the results of routine calculations that predict exactly the sorts of phenomena the theory was designed to explain. But, occasionally, the predictions of a theory can be quite unexpected. If these are later confirmed by experiment, then one has impressive evidence in favor of the theory. The notion of confirming a scientific prediction is, however, somewhat problematic because of the need for simplifications of the kind I have been discussing. To take another example, Newton's law of motion and gravity imply that if you drop two objects from the same height, then they will hit the ground, if it is level, at the same time. This phenomenon, first pointed out by Galileo, is somewhat counterintuitive. In fact, it is worse than counterintuitive. If you try it for yourself, with, say, a golf ball and a table tennis ball, you will find that the golf ball lands first. So, in what sense was Galileo correct? It is, of course, because of air resistance that we do not regard this little experiment as a refutation of Galileo's theory. Experience shows that the theory works well when air resistance is small. If you find it too convenient to let air resistance come to the rescue every time the predictions of Newtonian mechanics are mistaken, then your faith in science and your admiration for Galileo will be restored if you get the chance to watch a feather fall in a vacuum. It really does just drop as a stone would. Nevertheless, because scientific observations are never completely direct and conclusive, we need a better way to describe the relationship between science and mathematics. Mathematicians do not apply scientific theories directly to the world, but rather to models. A model, in this sense, can be thought of as an imaginary, simplified version of the part of the world being studied, one in which exact calculations are possible. There are many ways of modeling a given physical situation, and we must use a mixture of experience and further theoretical considerations to decide what a given model is likely to teach us about the world itself. When choosing a model, one priority is to make its behavior correspond closely to the actual observed behavior of the world. However, other factors, such as simplicity and mathematical elegance, can often be more important. Indeed, there are very useful models with almost no resemblance to the world at all, as some of my examples will illustrate. Rolling a pair of dice. If I roll a pair of dice and want to know how they will behave, then experience tells me that there are certain questions it is unrealistic to ask. For example, nobody could be expected to tell me the outcome of a given roll in advance, even if they had expensive technology at their disposal and the dice were to be rolled by a machine. By contrast, questions of a probabilistic nature, such as how likely is it that the numbers on the dice will add up to 7, can often be answered, and the answers may be useful if, for example, I am playing backgammon for money. For the second sort of question, one can model the situation very simply by representing a roll of the dice as a random choice of one of the following 36 pairs of numbers: 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 5, 2 and 6,